Hello and welcome to Chapter 14, Code and Actions, where we're going to be talking about AI augmented platforms. So to start with, what we will be doing is, as always, going and installing the required AI Python packages and Olama, and then go from there. So let's actually start getting into this process. Going into Chapter 14, opening my terminal, and this is where I'm. All right, so first thing I will do is go ahead and install all the Python package requirements, which are here. So I'll go ahead and install all of that. My case is a lot of it is installed, but yeah, it went ahead and did anything that was missing. Next thing I'll do is do an installation of Olama. Okay, so it is installed. If I needed to reinstall it, it said what I need to do. So now I want to make sure that my kind clusters are running because it's been a few days since I did chapter 4. So I'm just going to go back and check if kind clusters are running. So you can see that my kind cluster, the platform dev is running. So I do not need to create the cluster or get the nodes. If that's not the case, I would have to go and create the cluster. So in this case, I don't because my cluster is there. Now the next thing to do is to go and export the secrets from Bitwarden. And the secret we are really looking for in this case is my Anthropic API key. We're going to be using Anthropic as well as a mock mode. So for Anthropic, I need to set the key. So I don't know if I have it in Bitwarden, so I'm going to just check and see if it's available. So let me find my master password here for Bitwarden. It's loading the chapter 14 secrets from Bitwarden. Let's see if it's going to find that. So it could not find Anthropic API key, so I will go ahead and set that online here on the things when I'm ready to do that. So that's good. So now next thing to do here is to create a virtual environment. And this, we know we have done this in the past. So the way we are actually going to do our virtual environment is using this command. So you can see that VN is up and running. Now let's make sure that we run our requirements one more time. Make sure that everything is good to go. I think they said within the virtual environment, things are ready to go. Now, let's get into the core of chapter 14 now that we have done the basic installation of everything. So chapter 14, as we discussed, brings together the AI and agentic capabilities into the platform engineering workflow. So as you read in the chapter, each script demonstrates a different facet of how intelligent automation can reduce toil, speed up incident response, and enforce safety guardrails. All of these things are happening while there is a human in the loop. So the demos that we have here that you will be running sort of shows the progress from that foundational RAG, retrieval augmented generation, through that multi-agent orchestration, going into governance and observability, showing you that the full life cycle of building, deploying, and monitoring AI augmented platform tooling. So as you read in the book, it's not about teaching you how to do AI or what AI is. That is a different conversation or different reading that you would have to do. But what I'm really talking about in this chapter is about applying those core concepts of AI and agentic into the platform engineering space. So that's basically what we're going to do. The first thing we will be doing is called RAG pipeline. So let's pull that up and take a look at the script first. It's under platform chatbot. RAG pipeline. So let's look at that first. So what this script does is that this is a full RAG pipeline built on LangChain and ChromaDB. And I've explained that in the chapter. So it chunks the platform documentation, embeds it into vector store, and retrieves that most relevant context before prompting an LLM to answer questions. So this is like a typical use case that you would have in the platform engineering space. So the AI capability here is that grounding, right? Instead of hallucinating, the model answers strictly from your own documentation. So the script displays prominently the mode live when the Anthropic Claude, when you using Anthropic Claude, or the mode would be mock while running without the API key. And I'll show you both as to how it works. And while we are running that, you can also see the banner at the top saying if it is, whether it is using the live model or a mock model. So let's go in and install, run this. I will go ahead and try and run this one. And remember that I have not set the Anthropic API key, so it is mod. Mode is mock, so you can see that no LLM API key or LangChain Anthropic is installed. So what it's doing is it's actually having a query, and it's there is a mock answer stored, which says that whatever the response that you stored is there. Now, let's actually set the Anthropic key and then see how this looks. So I'm going to do Anthropic API key equals, and I'm going to make sure that I sort of delete this part where I'm actually setting the key so that you don't see the key. But once you have done this, you would have to come back and, once you get the key from the Anthropic site, you would have to add your key here. Now let's look at the same thing with the Anthropic key set. So let's see what it's trying to do. So you can see that it is now using the Anthropic API key I set, and it's using the Claude Sonnet. And based on that, it's answering that question that I had here, which was how do I deploy Kubernetes? So as you can see, now this is really coming from Anthropic. So this is where that power of AI is there. You don't have to use Anthropic. In this code, it's very easy for you to change your Anthropic to OpenAPI or whatever you want to do. But at least this gives you a starting point as to how you want to do it. And you also saw the mock mode where you could run this whole thing without having a key so that you can just use it for learning. But obviously, the data that you're going to get there is going to be canned data, so it's not going to be true AI. Okay, so for the rest of this code and demo, I'm going to be using or running this with existing Cloud LLM so that you would see this data directly coming from the wherever it needs to come from. Okay, so let's look at the next one. The next thing that we are actually going to be doing is looking at indexing and querying documentation. So to do that, we will again go back to the code first. And we will be first pulling out this RAG pipeline, which we just did, RAG platform docs. RAG platform docs. Okay, so this is what we are actually going to be executing next. So this is more or less the standalone RAG demo. So indexes 5 sample platform documentation. What we are doing, as I described in the chapter, is like deployment, monitoring, scaling, security, and troubleshooting using TF-IDF, for similarity scoring. So when you ask a question, it ranks every document by relevance, retrieves the top 3, and composes an answer grounded in the actual text. So these are the kind of powers that you can see from AI. So what the AI will be highlighting is the RAG part, the technique that turns a generic language model into one that knows your platform specifics. So that is how this demo would look like. So we will do the not RAG pipeline, we'll do the RAG platform docs. This one. Okay, so as you can see, what it did when we asked it to do RAG platform docs here was It is a live mode. It actually connects to Anthropic cloud and that actually gets the data that it's looking for. So you can see various questions that's being there. What monitoring tools are available? It tells you what's available. Well, my service has high CPU usage. How do I fix it? So these are the kind of problems typically your developers would have, and that is what this can do. So you can already see the power of how this works. Now, the next thing we'll be looking at is the script called incident triage. So let's go back into that. So incident triage.py, that script I have here. So what this does is that this is more like a three-stage AI pipeline. So it does three things: triage, diagnose, and remediate. So it ingests raw alerts alongside logs, metrics, and recent deployment data, then uses pattern matching and confidence scoring to identify the root causes. So the agentic capability is a multi-signal reasoning. The agent correlates evidence from different sources to produce a diagnosis with a confidence percentage and generate a runbook of the remediation steps. So that's how it sort of works. So let's see how that one works right now. We'll run the incident triage we just looked at. And again, we're going to run in the live mode. We are not, so we're using Plot Sonnet, not using the mock. To do the mock, very simple. Turn off your the variable, and then you can essentially run this. So you can see this basically did what it's supposed to do. So essentially, it looked at the incident and it did the triage. And after doing the triage, it did the diagnosis, and then it actually went ahead and did the remediation. So here are the remediation activities. So it went ahead and did the uh, remediation there. So it said that this is how you can actually check and see if the service is fixed. So that is the third one. The next one we will look at would be a multi-agent incident response. So for this one, there is a script called, let me see where that is, incident agent. So the incident agent. So this is that incident agent response system. So what this does is that this orchestrates a simple incident response lifecycle. So what would be the lifecycle? So you start with detection, investigation, planning, and execution. It then sort of handles that multiple simultaneous incidents, assigns severity, tracks status through each phase, and produces a summary showing how many were investigated, planned, and resolved. So that is a comprehensive system that you would find in doing that. So let's see how that would work. I come back here and I run my script that we just looked at, which is incident agent. So I run the incident agent and you can see that uh, it's actually found, it looked up the incident and then it basically says that, oh, here is what the incident is, started triaging. And then essentially that's a detection part. Then it sort of investigates, plans, so proposed action where it's planning, and then it goes ahead and runs it, and then eventually resolves it. So you can see that there are three incidents, three total incidents, two of them critical, and three actions were approved, and all three were resolved. So you can go through the script and see how that sort of works. Now, the next thing to do would be demonstrating your alert correlation. So to do the alert correlation, let's look at the alert correlator.py, as I mentioned in the book. Alert correlator. Okay, so let's see what this alert correlator does. So, uh, so in a typical platform, a single outage fires dozens of alerts. So the script uses again TF-IDF, similar, sort of similarity scoring, and that's a consistent way of doing this, and a time window grouping to cluster related alerts. So when I say related alerts, would be things like your high CPU, your OOM kills, and the pod restarts on the same host, all of them into a single incident. So the AI capability is noise reduction. So here, instead of three separate pager duty tickets or whatever your alerting system tickets, your on-call engineer sees one incident with a correlation score essentially showing how tightly these alerts are related. So that's what the script would do. Okay, so let's look at that and run it. Okay, so it went through the same incident, found that, then it started creating that correlation, as you can see. So you can see the separate correlation score for each of them. And you can see that the average correlation score is there and the noise has been reduced by 25%. As I said, that is really the goal. The noise reduction is truly the goal in a case like this. So next thing is to see how we could run a multi-agent system. So in the book, I had a reference to that about like what are multi-agents. Since this book is not about AI, I'm not going into so much of details about describing how to build lots of these autonomous, multi-autonomous agents that actually work together. But I've given a pretty decent explanation of how that works. I've given you an architecture there too. So let's look at that agent first. Um, let's look at the agents, the multi-agent system.py. So what the script does is this is sort of think of it like the most advanced agentic demo in the book. So there are four specialized agents collaborating in a supervisor pattern. So there is this investigation agent that gathers the data that you can find here. Then it sort of that gathers data and sort of identifies the symptoms. Then there is a planning agent that proposes a remediation plan with the rollback steps. And then there is an execution agent that carries out the approved actions, and a supervisor agent sort of orchestrates the whole workflow while enforcing safety constraints. So every action is logged into more or less an immutable audit trail. So the agentic capacity is is sort of exposed by the fact that you have autonomous orchestration with human in that loop approval gates. For example, there are some dangerous steps there, like things like modifying your resource requests and all that. So those things would require a manual explicit approval before execution. So let's see how this one would work. So let's see what it did. Okay, so you see this running here. And I mean, there are obviously some minor warnings from the script itself, which you can fix if you would like. But it starts investigation of pod crash loop, and then it goes through the whole process of investigating that. And then it comes up with the remediation workflow result. And then it provides you a complete audit trail of how that works through that process. And then you have that. So essentially, what you're seeing is that investigation, planning, and the execution with audit trail and approval gates. Now, another thing I've spent some time in the chapter is about demonstrating the AI guardrails. So let's look at that script first. So this AI guardrail script, what this does is that it implements a safety framework with five severity levels. So the severity levels would be like read only. So what is that? I mean, low severity, medium, high, and critical. So there's a per agent action, allowless, confidence thresholds, and a human approval workflows all built into it. So the guardrails I talked about are all enforced in the code. It's not the prompts. So no matter what the LLM suggests, the system blocks the actions that exceed an agent's permissions or fall below the confidence threshold for a given severity level. And this is exactly how you want to establish the guardrails. You don't want to leave that to the LLM completely. So what the AI does here is that it sort of highlights its deterministic safety boundaries around those non-deterministic AI outputs. So let's look at how this works. Okay, so see, not that here. Yeah. So you can see that guardrails happening here. So first it's sort of testing the guardrails with the sample actions. So it's saying, what's the safety, if it's approved, what's the execution of it. You see that for each of those five steps I talked about. and they can see how many actions been taken, and then what was the approval, and how many audit trail entries are there. So you can get all of those things right from the script. And my goal is that for you to get a starting point on it so that you can use these scripts to learn further as to how this would work and ensure that you extend that to what you would really need it to be once you understand how this works. So next thing we will look at is deploying the AI governance alerts. So let's see where that is. AI governance alerts, yes. So this is what you want to really look at and see how that works. So basically, this YAML defines 7 Prometheus alerting rules, built for monitoring AI agents in production. These would be like low confidence scores, high human override rules, error spikes, latency degradation, and SLO breaches. So these are operational guardrails. So again, you have earlier we saw that how it can prevent bad actions at runtime. These alerts, as a difference to the earlier one, catch a systemic drift. So like when a model whose confidence has been declining for a week, the AI governance capabilities sort of treating that agent health as a first class SLO, just like your uptime and latency we discussed earlier in the book. So to do that, we need to do some setup. Let's see if we can go ahead and make all of that happen. First thing we will do is to create the monitoring namespace. So you can see it's already existing from our prior work. Then go ahead and add the health charts. That's existing too. Then we'll just do a repo update. All right, it's updated. Then you can the Prometheus stack. So this is good. Basically, it says that it's already there, so you don't want to like rewrite that. So this is perfectly fine. If you didn't have one, it would have installed that. Now, once you have done that, you can just go ahead and apply the AI governance alerts we looked at earlier. So it created the SLOs, and then it can get the Prometheus rules. So you can say that, yeah, AI governance alerts is running. So you can see that this rule is now created with like all these alerts and the SLO definitions that we set there. So next thing we can do is to run the observability demo. So there is an observability.py script I created. Should be somewhere here. Let's see where that is. It's under AI governance observe. Yeah, I think this is where it is. Okay, so you can look at this observability.py script. So this script shows that track agent call decorator pattern for instrumenting AI agent calls with Prometheus metrics. So every agent invocation records latency histograms, confidence gauges, success failure counters, human override flags, and all that. So the AI observability capability is making agent behavior measurable. So you can build Grafana dashboards that show exactly how your agents are performing over time. Most cases, that's what you do. And obviously you're doing that to ensure that you know where they need tuning. So to do that, you can go ahead and run this first. Okay, so you can see that it ran. It basically collected the data, found all the current status, and all this different data that we said is going to be pulled out from there. So primarily latency, confidence, override rates, and override rate and errors. Okay. Now we can look at measuring the AI impact. So there is a script for that, measure AI impact.py. You can look at here. So what this does is that this generates a side-by-side comparison of AI-assisted versus manual incident handling. And this would be very powerful for you as you learn this and as you're really trying to roll this out within your organization. This would be a very powerful tool that you can expand further. It sort of measures MTTR and alert acknowledgement time and the diagnosis speed. You can of course extend it to anything you want. The AI capability is the quantifiable value, showing the stakeholders concrete numbers like I had like 10x% of MTTR reduction and Y% is faster diagnosis and all that. So that is the whole purpose of this. So let's actually try running this. So you can see that there is a side-by-side comparison of each of these things. What happens in manual, what's the AI assisted, what's the improvement? Similar for MTTR, for alert acknowledgement, and the diagnosis speed. So you can see the kind of improvements that is brought out. And these are simple ways in which you should be able to show that value of what this does. Now, the next thing we will do is look at this idea of runbook automator that we discussed in the chapter. So what runbook automator does is that it parses the human authored markdown runbooks. So you might have a .md file with certain runbook data so that'll actually change that into very structured and executable steps. This step is classified as diagnostic action and notification and validated for safety. So the automator detects that the destructive commands like remove rm minus f, RF or delete or kill and sort of blocks them until a human approves. So you don't really want to have AI run your kill and RM and delete and all that. That's one thing that you would do. But again, you can obviously use the kind of data that you have in your enterprise to make this smarter. So the AI adjacent capability is turning that tribal knowledge, whatever that you have in the run books that sit in your wiki pages or Confluence or something, into automatable workflows with built-in safety checks. So that is what this one would do. So let's run this. So you can see that it went ahead and did the runbook automated demo, and it looked at multiple steps. And for each of the steps, it looked at what is happening, if it is running Postgres, and how much is the disk space is there, and all that kind of things. So essentially this becomes something that is far more like automatable workflow as opposed to more of what you have in your documentation. So this is essentially that set of things that I've explained in the book. As always, we will go ahead and conclude by looking at running the tests on this one. So we'll run a test agents. So in this case, they had 15 tests. So just make sure that each of these 15 tests are running, and and everything is passing. So that basically concludes the chapter 14 code in action. Thank you.